Right, welcome again to the new lecture, lecture number 11, chapter 12, thermodynamic property relations. So let's review previous lecture first. In previous class, we discussed Joule Thomson coefficient that is used for the throttling process to decide whether a process during a throttling process whether the temperature will increase, decrease, or remain constant, and then we derive the relationship for change in enthalpy, change in internal energy, and change in entropy of the real gases, right? So in this class, we'll try to solve a couple of numerical problems related to the previous chapter, previous topics. Let's see the first example. Now consider 1 kilomole of argon gas available at, let's say, 300 Kelvin, initially confined to one side of a rigid insulated container divided into equal volumes of 0.2 cubic meter by a partition. The other side is initially evacuated, the partition is removed, and the argon expands to fill the entire container. So previously the container was divided into equal part of 0.2 cubic meter volume and there was a partition. So let's say that partition is removed, then the argon gas will expand to fill the entire container. Now, using the van der Waals equation of state, determine the final temperature of the argon in Kelvin. Right? Then repeat the same problem using the ideal gas equation of state. Use the properties of the argon like Cv is equal to 3 by 2 of the R, which is R is a gas constant. Critical temperature for the argon is given and critical pressure for the argon is given. So based on this given data, and we also know the van der Waals equation of state, P pressure is equal to RT by V minus B minus A by V square, where A and B, they are the constant, and A is equal to, further, this is another constant, which is a function of different constant like 27 is a constant, 64 is a constant, R is a constant, TC is a constant, PC is a constant. So if we see in graphical form, let's say this was an rigid and insulated, let's say, container, right? And it was partition of volume 0.2 cubic meter and 0.2 cubic meter. In one partition there was argon gas which is at 300 Kelvin and 0.2 cubic meter volume. Now if we remove this partition, then obviously the argon gas will expand to the whole container. Now the new volume is 0.4 cubic meter. The question is, try to calculate the temperature of the argon, this final state, by considering consider the argon gas as van der Waals equation of state, apply that, and then repeat the problem by using ideal gas equation of state. So let's see. So in this example, since the container is rigid and insulated, so that means heat transfer into the container or from the container is equal to 0. Similarly, work done on the container is also 0 because there is no movement of the container since this is a rigid container. So that's why there is no change of volume, no change of pressure. No, there is no expansion. There is no mechanical output so that any system cannot move. So the work done is also 0. Right, and if we ignore, there is no change of the height, kinetic energy effect can also be ignored. So if we apply the fundamental law, first law, then we know the change in the heat transfer is equal to the internal energy change plus work done. So if we put the value, the first term, this is 0, work done is 0, so only remaining term is change in internal energy, right? That's equal to 0. Now we know that the container is rigid and closed, therefore mass and volume of the gas is constant. So if the volume of the gas is constant, we can also specify this in terms of specific internal energy. So specific internal energy is also equal to 0. Small delta U is equal to 0. And for any two state, we know we have a general relationship that was derived in our previous lectures, that change in internal energy generally is a function of temperature, pressure, and volume. So this was the relation that we derived in a previous lecture. So this change in internal energy for this example is equal to 0. So that means in order to calculate that value, we need the value of the first term as well as the second term. Now the second term is basically T times partial P by partial T at constant volume minus pressure. That means first of all we need to calculate this term, and this is only CV. We know this that CV value is given 3 by 2 R. So this term is not a problem. Basically we need to calculate the second term. So let's start with this one. I mean, let's say the first part is using the van der Waal equation of state, and we know that van der Waal equation of state is P is equal to RT by V minus B minus A by V square. So that means we need to calculate this term. I mean, we have to take the derivative of pressure with respect to temperature, keeping the volume constant, right? This is the first term, the derivative of this. And then we have to multiply, I mean, we need the full term, T times this term minus P. So if we multiply with the T as well as minus P, so we put the value of the P as well. And if we simplify, this term will be cancelled out. So this minus minus will be plus. So the remaining will be A by V square. So this whole term is equal to A by V square. Now we can put these values in the general equation, that was equation 1. So if we put this equation, I mean the first one is CV times dt. So CV times dt from state 1 to state 2 plus, and this whole term is equal to A by V square into dV. So for any two state, if we simplify, then we'll get 3 by 2R T2 minus T1 plus A, and this is 1 by V1 minus 1 by V2 is equal to 0. So you can see from here, basically, we know the initial volume. Initial volume was equal to 0.2, and the final volume when the partition was removed, that was equal to 0.4 cubic meter. And A is a constant. We know the A is given. R is a constant, and we know the initial temperature. So we can calculate unknown. So if we put all the values, we'll get this value. So the change in temperature between the two states is minus 27.43. That means there is a decrease in temperature. So that means if the argon gas was available in partition, let's say this was partition. So if we remove that partition, then there will be decrease in temperature. And how much will be the decrease in temperature? Minus 27.43. We know the initial temperature, that is equal to 300. So if we put that value, so the final temperature will be T2 will be equal to 272.6 Kelvin. So this was calculated using basically the real gas equation, right? The van der Waal equation. If we solve the same problem using the ideal gas equation, we know that ideal gas equation is a function of temperature only. I mean, but we have to adopt the generalized form of change in entropy. But the equation for the ideal gas equation is PV is equal to RT. Similarly, that term partial P by partial T at constant volume is equal to R by V. And the whole total term is T times partial P by partial T at constant volume minus P. So if we simplify, that's equal to 0. So that means the second term is equal to 0. I mean this term, the second term is equal to 0. So that means the change in entropy of the ideal gas is a function of temperature only. So if we put those values, 3 by 2 R T2 minus T1 is equal to 0. So that means change, this is 0, right? And so that means there is no change of temperature. Delta T is equal to 0. So T1 is equal to T2. So the entirely different calculation by just changing the real gas to ideal gas. So that's why the values that we calculate using the real gas, that are entirely different than the values we calculated using an ideal gas. Although calculation using ideal gas is very simple, but as long as they are based on some logic, some assumption, they can be acceptable. But if they are not based on certain assumption or certain logic, they are much away from the real behavior. So let's try to calculate another example. This example 2. In this example, let's say nitrogen enters a turbine operating at steady state, at 100 bar and 300 Kelvin and exits at 4 bar, 40 bar and 245 Kelvin. Determine the work developed in kilojoule per kg of nitrogen flowing by considering ideal and the real behavior of nitrogen gas. The heat transfer with the surroundings can be ignored. And part B is calculate the rate of entropy production in kilojoule per kg per Kelvin. So that's very simple, Nandu. I mean, that's like a expansion of the nitrogen gas in a turbine. And we know that, let's say, this is a turbine and we have state 1. At state 1, nitrogen is available at 100 bar and 300 Kelvin. So after expansion in a turbine, there is a drop in pressure and temperature. Pressure from 100 as a result of the expansion, pressure is 40 bar and there is a drop in temperature as well. 245. So because of this expansion, obviously we'll get some work output. So the question is, for the nitrogen gas, calculate this work output by considering the ideal behavior as well as the real behavior so that you can compare between the work output calculation using ideal behavior as well as real behavior of the nitrogen gas. In part B, I mean, let's say there is a entropy production. I mean, let's say from here to here, this entropy production. Also calculate the change in entropy production using ideal behavior as well as real behavior. So let's start the problem. So we know that the output of the turbine, I mean the expansion as a result of the expansion is basically equal to the difference of the enthalpy. I mean H1 minus H2. Now this change in enthalpy can be calculated using an ideal behavior. It can be calculated using real gas behavior. So first part is to calculate based on the ideal behavior. So if we consider the ideal behavior, then the properties of the ideal gas for nitrogen gas is available in the table that are given in the appendix of that book. So we know from that table A18 we can use the properties of the nitrogen as an ideal gas. So at state 1, temperature is 300 Kelvin, so we can read the property. That star represent the properties as an ideal gas. So H1, similarly at state 2, I mean at outlet of the turbine, we know temperature is 245 Kelvin, so we can read the enthalpy H2 is equal to 7121 kilojoule per kilomole. So now the difference of the enthalpy using an ideal gas behavior is H1 minus H2. So that's equal to 1602 kilojoule per kilomole. But we need to calculate in kilojoule per kg. So we have to divide this value with the molar mass. Molar mass for the nitrogen is 28. So if we divide that, then the value is 57.2 kilojoule per kg. So that's the work output of the turbine as a result of the expansion of the nitrogen when we consider nitrogen as an ideal gas, right? Now, in part B, it says calculate the same work output using real gas behavior of the nitrogen. So if we consider part 2, real gas behavior, then we know that the change in enthalpy between the two states when we consider real gas behavior is equal to the difference of enthalpy as an ideal gas minus this term. This term is known as enthalpy departure. This term is known as enthalpy departure. We have derived this formula in our previous class. So for this one, basically we need ZH1 and ZH2, ZH2 and ZH1. This is basically ZH is basically enthalpy departure coefficient. This is enthalpy departure coefficient for stage 2. This is enthalpy departure coefficient for state 1. And how can we get this ZH2 and ZH1? And this was for kilojoule per kilomole. If we divide with molar mass, then the whole term will become kilojoule per kg, because in the problem solution, it is required to calculate in kilojoule per kg. So from this equation, what we need is we need ZH1 and ZH2. And how can we get these enthalpy departure coefficient? First of all, we need the value of the reduced temperature and the reduced pressure. So we can get this reduced temperature as well as reduced pressure for state 1 as well as for state 2. what we need is, we know that the reduced temperature at state 1 can be calculated by dividing the given temperature with the critical temperature. Similarly, reduced pressure can be calculated by dividing the given pressure with the critical pressure. So we know now TR1 and PR1. So if we know these two values, we know from table A29, if we know that, we can read the value of ZH1, which is called enthalpy departure coefficient at state 1. Similarly, for state 2, we can get TR2, reduced temperature at state 2. The given temperature divided with the critical temperature. Similarly, reduced pressure at state 2, given pressure is divided with the critical pressure. So if we know the reduced temperature, reduced pressure, we can get ZH2, enthalpy departure coefficient at state 2, again from the figure A29 that was explained in our previous class. So once we have all these values, the remaining is just put the values like we know 1 by 28 and H1 minus H2. We already calculated that using an ideal gas, right? This one minus, and we know the value of R 8.314. We know the critical temperature of the nitrogen, and ZH1 is 0.5 and ZH2 is 0.3. So if you simplify, the value comes out to be 50.1 kilojoule per kg. So this is the work output of the nitrogen as a result of the expansion in the turbine. So if we compare that, in case of ideal gas, this was 57.2, whereas the actual or real behavior gives the value of 50.1 kilojoule per kg. So almost 7.1 kilojoule per kg. So this is a huge difference, right? So you can see the impact how the calculation vary if we just change the real gas behavior from an ideal gas behavior. Similarly, in part B, we need to calculate entropy production. Using the real gas as well as using the ideal gas. We know that from the previous lecture that similarly we can get the change in entropy is equal to the ideal gas entropy change minus the departure from the real behavior. So this is R ZS2 minus ZS1. Again, for this one, you can see, for in order to calculate the real gas behavior, we have to calculate the value of the this is entropy departure coefficient. Previously, that was enthalpy departure coefficient. Now this is entropy departure coefficient for state 2 as well as for state 1. So first, let's calculate for the ideal gas. For ideal gas, we know this is just to change the unit. If we divide with 1 by n, that will be kilojoule per kg per Kelvin, right? So for the ideal gas, we know that you have calculated in chapter 3 how to calculate the change in entropy of the ideal gas. That's equal to S star at state, this is standard entropy at state 2 minus standard entropy at state 1 minus R ln P2 by P1. So this we can read from the property table, value of the entropy at temperature T2, similarly value of the entropy at temperature T1, that's the constant for R. For nitrogen, similarly, that's P2 is given, P1 is given. So if we put all the values, then and simplify, then the value will come out to be 1.711 kilojoule per kilomole per Kelvin. Right? So that's the change in entropy when we consider the ideal gas behavior. So what if we calculate the real gas behavior? For that, we need the value of ZS2 and ZS1. For that, first of all, we need the reduced temperature at state 1, and if we know reduced temperature, then we can, and reduced pressure we already calculated in our previous slide. Similarly, we can calculate at reduced temperature 2, the value is 0.14. We have to read that value from the figure A13. So if we put these values in the above equation and if we simplify, then the change in entropy for the real gas behavior is a 0.082. So you can see a difference. There is a huge difference. The ideal gas change in entropy is 1.711, whereas the real gas behavior, it's 0.082 kilojoule per kg per Kelvin. Right? Now, this is another example, example 3. In this example, consider a gas whose equation of state is P times V minus A is equal to RT, where A is a positive constant. The question is it possible to cool this gas by throttling? So if we use this gas for a throttling process, let's say in a capillary tube or in a valve, can we produce cooling if we use a throttling process for this gas? So who will decide? I mean, what's the criteria for producing cooling, for producing heating, or for the isothermal process? Yes, Joule Thomson coefficient will decide that whether the throttling process will produce cooling, heating, or it will remain constant. I mean, the value of the Joule Thomson, if the value of the Joule Thomson coefficient is negative, then the heating process and temperature increases as a result of the throttling. If the value come out to be zero, then that's an isothermal process. If the value is positive, so that's the cooling will produce for that gas, right? So we know that the value of the Joule Thomson coefficient we derived in the previous class, that's equal to minus 1 by Cp V minus T times partial V by partial T at constant pressure. So basically we need to calculate this value. This value will decide whether this gas can produce cooling, heating, or then the question is it possible to cool this gas? So let's try to put the value of the V and then this term and then simplify, right? So the equation is P times V minus A is equal to RT. So P times V minus A is equal to RT. So from here volume will be equal to, volume is equal to RT by P plus A, and then let's say we take the derivative of V with respect to T at constant pressure, so that will be R by P. So if we put this value in this equation, then we'll get minus 1 by Cp V minus T times R by P. So if we simplify, this is again, this term is again minus V plus A. I mean, if we simplify this one, right? RT by P. This is RT by P. So this will go on the other side. So V minus A. So if we put this, and if we simplify, this is equal to, this will be cancelled out, so remaining will be minus A by Cp. So we know that A is a positive constant. So A is a positive constant, and we also know that Cp is always constant, and specific heat of a gas is always positive. That means as a whole, this value is a negative, because if this is positive, and this is negative, so this value is negative. So what it indicates that this value is less than zero, so negative values. That means this gas will always produce heating. So if we use, let's say, we use this gas, I mean this gas whose equation of state is this one. That's if we use this for the refrigeration process, so this is not suitable for refrigeration process, because in a capillary tube or in a throttling process, it cannot produce cooling, right? So I hope you understand. Gas cannot be cooled by throttling process. So that's the end of chapter as well, chapter 12. So for you, I mean for the coming quiz and assignment session, please drive all the thermodynamic relations that we exercise in the class. And for numerical problems, let's say related to Maxwell relations, please attempt problem 1214E to 1217. Similarly, for Clapeyron equation, 19C to 21. For Joule Thomson coefficient, please practice 52C to 56. And for real gases, calculating dH, du, and ds, please practice 65C to 1272. Right, so that's the end of this class. Hope to see you in the next class.